Thank you, Ernst, for the great introduction. Good afternoon, everybody over there. It's good morning here, and thank you for having me in this GNI International Symposium on Artificial Intelligence for the Built World. I wish I could be there in person, and given the circumstances, I'm glad that I'm able to join via Zoom, but I'm very much looking forward to visiting there sometime when we are able to travel again and meeting you all in person. And congratulations also on your on the formation establishment of your institute. In the next half an hour or so, I'll talk a little bit about our research on using AI but making a context-aware usage of AI to support infrastructure and facility management. Before I do that, I'd like to maybe give a little bit of an overview of Carnegie Mellon. I'm from Carnegie Mellon, and it's located in Pittsburgh, Pennsylvania in the United States. And this is our campus. And as you can see, our campus is very small compared to, let's say, Stanford, that I did my PhD in. And there are some benefits of having a small campus where we collaborate quite a bit across different disciplines. So in my talk today, almost all of the research that I'm going to present is done in collaboration with Robotics Institute, Computer Science, and Electrical and Computer Engineering, as well as other faculty members within the Civil and Environmental Engineering. I also want to give a little bit statistics about Carnegie Mellon, again, just to put it in a context of where I'm coming from. So Carnegie Mellon has been consistently ranked as #1 in computer science and #1 in AI and #4 in College of Engineering. The reason that I'm saying these is, again, AI and the computational thinking is very much embedded into everything we do. And civil and environmental engineering is no exception. It's embedded in the courses that we teach, as well as many of the research projects that we do. So going from that high level to who am I? So I'm a faculty member in civil and environmental engineering, and I have very deep connections to this discipline and completely passionate about civil engineering. So I come from a perspective of, as Martin was saying, we have important problems that we need to solve in civil engineering, and AI is one of the tools that could help us solve those problems. Really truly coming from the domain perspective. So some of the things that I might be presenting today might be blinded by that perspective that I have. Another aspect is that in addition to being a faculty member, I co-founded a company that uses AI for supporting facility management. And the reason that I'm mentioning this is that towards the end of my presentation, I'm going to give a couple examples where we try to deploy AI in a variety of facility management scenarios and some of the benefits that we have observed when we combine contextual or domain information with the AI algorithms. So some of you who have heard me speaking before, I always start with more or less this slide because I'm always baffled by how some of our engineers, some of these simple questions like, are there any deviations in construction sites? Or what is the valve to shut off the water? Or how well is my HVAC system performing? These very simple questions sometimes becomes very challenging for our engineers and managers to answer because of the complexities around the building environment and also the heterogeneous and the distributed nature of our data sources. So what ends up doing is that many of our engineers and managers end up making decisions in the dark. And as you see, these questions are not civil engineering questions. These are information questions. And we need to be able to answer these questions at this day and age in a objective manner and in a reliable manner, so that our engineers and managers can actually focus on what they are good in doing, rather than trying to search for information or try to make assumptions, and as a result, maybe not be able to make optimum decisions. Of course, we want to move, we don't want to just answer those typical asset management questions, but we want to move away from this reactive the reactive way that we manage our facilities to more proactive and predictive manner. We want to move away from subjective decision-making to a more objective decision-making. We want to be able to move away from decision-making in the dark to having more complete situation awareness of a facility or a construction site. And we want to move away from treating our systems as a single system, let's say the HVAC system or our road systems as a single system, towards more treating them as systems of systems that are interacting with other physical systems and the social systems around that. And we want to be able to do these autonomously, right? So that's where we want to go towards. So when we think about autonomy, we see automatically, autonomous cars come to mind, right? So when we think about a car, a medium-sized sedan has about 400 sensors on it. And we treat this car as a giant computer, right? So when we try to do diagnosis and figure out what is going on with the car, we hook up an intelligent diagnostic tool because we know that it's a giant computer. And currently we know that autonomous cars are here, right? So the autonomy is already achieved in the car domain. When we look at buildings, we do see a similar amount of sensors, right? So a 60,000 square foot building have about 21,000 data points on it. But when we start treating, when we look at those buildings, we don't typically see them as giant computers. And as a result, we end up basically going back to the manual diagnosis and maintenance. So this is almost like using a hammer to fix your computer, right? So our building is a giant computer, but we rely on these manual processes. And autonomous buildings are still in the future, but not quite there yet. And this problem, this simple manual diagnosis and maintenance for faults in the buildings, cause about $50 billion energy waste in the US commercial buildings, because we are not able to identify all the faults in a facility. And many of those, though undetected, continue to waste energy. And when we kind of extrapolate that number to the whole world, it's about actually these faults in our HVAC systems can cause about 4%, contribute to the 4% of the world's energy usage. So, this is a significant problem. So then the question becomes, why aren't we there in terms of, achieving these autonomy? Well, the buildings bring some certain challenges that car industry doesn't have. And many of you are familiar with that, right? So each building is unique. Each building has unique complex control logic implementations to manage their interdependent building systems. And even in the same building, same components behave very differently. Depends on the context of usage, depends on where they are serving. And I'll give an example of that later in the talk. Not only each building is unique, these buildings also change over time, right? So these changes, the usage of the facilities change, the layout changes. And you can think about this as, let's say you got a sedan car and then you turn it into an SUV and then turn it to a truck and then turn it back to a sedan, right? So those, of course, don't happen in the cars, but it happens regularly in buildings. And the third aspect is that the owners and users are deeply involved in our facilities, right? So we can override some of the implementations that happen. If we don't like the way some building controls are working, we might even fiddle around with the sensors that are in the space. And we also can act as sensors. We can provide more information or more data about the facility to help determine what might be going wrong. So with all these challenges associated with buildings, we need to think about, how we can achieve autonomy while addressing these challenges. So many of these challenges addressing of these challenges require data. And, the good news is that we have several data sources already in place, right? We have building information models that virtually depicts the facility. We have sensor data in the buildings, in our building automation systems, and we're collecting hundreds of megabytes of data per day from these sensors on a small to medium sized building. If we want to, we can take additional sensors out there, right? Like 3D imaging sensors, and within minutes or within hours, we get gigabytes of data. And now we also have people doing things around either construction site or facilities, continually telling us what is happening in a facility, like I fixed this part of the facility, etc. So, data sources are plenty, and these data sources provide an opportunity for us to understand what might be happening in our facility. So if we integrate these virtual models, like building information models, they provide context to all the data that has been collected at the job site or at the field, and hence we don't treat these data as just look at the data on its own, but we put the data within the context of the BIM to understand what might be happening within the facility. Similarly, these data sources provide an opportunity to continually update our BIM or our digital twin, so that it reflects the as-is conditions and becomes a reliable source for analysis. So we have been working on that nexus of integrating the virtual models with the sensor data, and then also using the sensor data to update the virtual models. So the three major questions that we have been working on over the years is, how do we create these digital twins of facilities that reflect the as-is conditions? How do we start from a reality captured and turn them into a digital model? And of course, this is not static, right? Change is continuous. Then how do we continue to update these digital models so it reflects the as-is conditions? The other research question that we have been trying to answer is that, as you have seen, there's not a single data source that's going to make our life, there's not a single magic bullet, right? So we need to be able to integrate data from multiple heterogeneous sources. So we've been looking into different data fusion approaches. And once you integrate them, what's the structure of that living information model might look like? That helps us kind of go from information to data to knowledge in a seamless manner. And finally, once you have that repository in place, how do we use that to derive actionable information? Anywhere from visual analytics to the detection and diagnostics approaches, and eventually getting into more prescriptive and predictive maintenance. So in this talk, I'll go over a couple examples on the first question and a couple examples on the last question. First question, in terms of how do we create these digital twins, there can be many approaches. We can take laser scanners out there and get point cloud data, but then we need to turn those points to BIM. Or we can utilize the images that are collected in the fields, but we still need to turn those images, these pixels, into information that is useful. So into some kind of a semantically rich information model. We can even use the drawings and the symbols in the drawings of old buildings and turn those into BIM. There are some specific challenges, and there have been many studies in all of these domains over the years. But there are some specific challenges that make this workflow from points to BIM or images to BIM a little a little more challenging for our industry than maybe some other industries. So as I mentioned, there have been many studies in this space from computer vision as well as in our domain. Many of the studies that exist and it claim shows these large high precision in their approaches typically have some assumptions that don't work well for our industry. So they assume that the data capture that we have are in clean and simple spaces. You see, there's no furniture, no clutter, no temporary objects in the scene. They assume that these scenes have rich and unique features, which makes the stitching of the scenes and object recognition a much relatively easier task. And when they talk about semantics, they're mostly talking about geometric model with some labeling rather than truly understanding the different components in place and the relationships between them. So the reality that we face in our industry is a little different than these assumptions, right? So we work in very cluttered places. Construction job sites is an example of that. We have also any other facility that is in use is an example of a cluttered place. We have very poor and similar features. So we don't have, most of the walls look alike and it's difficult to identify which one is which. And we definitely want to have a complete scene understanding of everything labeled and the relationships between them. So with the goal of supporting the reality, when we try to do points to BIM, we initially started with more data-driven approaches, and only to realize that it doesn't achieve the accuracies that we're looking for. So we pivoted from that and started incorporating the domain knowledge into those approaches, where we put some aspects about, walls are typically in the perimeters, and there's some vertical orderings, there's some containment relationships. And when we combine those, or we call it hybrid approach or contextual AI approach, then you incorporate the domain knowledge with the data-driven approach, then we were able to achieve much better results in this pipeline of turning points into building information models. Similar issues we faced in trying to turn images to BIM. These are random images that are collected at a job site. And what you can see is that they're collected for a purpose, but not for the purpose of updating a BIM. And as a result, they're looking at only one side of something to document what might be going wrong on that component specifically. And hence, there's not much overlaps amongst these images, which makes it very challenging to figure out even where these images are taken from, let alone create a full 3D model from that. There's intrinsic ambiguity due to this certainly unguided data collection, because different cameras, different ways of collecting data. There are repetitive scenes because we don't have unique features. It seems like we're seeing the same object, even though we might be looking at different things. And of course, on a construction site, there's also this additional challenge of dealing with the dynamic scene. Again, we tried more data-driven approaches initially and did not succeed. And we said, well, what if we start with them, maybe initially label each, start with each image and label each component, identify each component in an image, and then use that as a way to figure out where that image is taken from, and to start document what might be happening at the job site. And we use basically, regular uniformat hierarchy to figure out the objects in the scene, so that we would be able to deal with the dynamic nature of the construction site, right? A mezzanine might have slabs on it, and the slabs might have reinforcement reinforcements on that. Again, these approaches still has challenges, but allowed us to achieve a higher accuracy than a purely data-driven, purely pixel-driven approach for segmentation and reconstruction. So that was more on the trying to build up the digital twin of a construction site or of a facility. Let's say we have something like that, then how do we derive the actionable information? And in the next few slides, I'm going to focus back on these HVAC fault detection and diagnosis problem, as it's an important problem, but it also highlights some of the challenges and why we needed context-aware AI to address, an issue in our industry. So starting with why this HVAC problem is a challenging problem, I want to bring an example here. So what you're seeing here is two different, same set of components, dampers and supply fans, which is a subunit of an HVAC system, and behaving two different ways. So in the normal case, on the left-hand side, what you're seeing is the damper is 100% open, and the supply fan is providing an airflow to the space, a certain airflow to the space. And when the damper is 100% open, the supply fan speed is about 37%. So when there's a fault in the damper, which happens pretty regularly, the dampers get stuck. And let's say in this case, the damper got stuck 40%. The supply fan, by definition, because of the control logic and because of the requirements, is still trying to provide the same airflow to the room, but now working with 92% speed, right? So from the occupant perspective, there's no difference. There's no symptomatic issue here, and hence nobody will say that, oh, there's a fault in the system because the airflow is coming the same way in both of the scenarios. But what's happening behind the scenes is that you're, utilizing at least twice as much energy to be able to provide the same airflow because there's a fault here that is not detected. Oh, I'll just move. So then, let's say even if we detect the fault, right? So if we have a problem that the occupant says, I have a problem in my room because it's too hot, too cold, which is the common, complaints that we hear in facilities. Well, diagnosing that problem will be a bit challenging, right? So here is a control logic implementation of a single air handling unit. And what you're seeing is these sensors and control parameters create this spaghetti of, intertwined, loops and referrals and things like that, right? And on top of that, this control logic implementation is not openly provided to the building managers. So building managers don't know all of these linkages. Though even if they know, it would be very difficult to parse through these to figure out exactly what is going on, which component is causing the problem of the hot cold from in a specific room. The third aspect that was challenging in our facilities was that, well, we might say, well, yes, those are challenging, but the good thing with our facilities, we have lots and lots of data. And can we just train our model? Can we use like data-driven AI and train our model with one unit and then transfer the knowledge to the others? So we try to do that with 6 rooftop units, same manufacturer of utilized in the same building. So there's no different building issue here. And we said, well, we're gonna sit down and spend the next 2 months labeling the first rooftop unit's data and then train the model with that label, and can we transfer that then to the other rooftop units? And as you're seeing, it wasn't easily transferable, right? So, and the reason behind all of these is that even though it's the same manufacturer, the utilization of these rooftop units are different. This was a medical facility. Some of them were feeding to the operation room. Some of them were to the, to individual rooms. Some of them are offices. The way these units are being utilized throughout the facility was different. Hence, bringing back the need to say, okay, we got to put things into the context. We got to evaluate each of these components under the context that they're being utilized. So to do that, the first step is build up the context. And we spent quite a bit of time in how do we bring all of these different heterogeneous data sources available in the facility into a single platform where you can overlay, just like GIS, right? Overlay many of the data that is spatially collected in the facility, like work orders or pictures or sensor data into the space. So at least you have an integrated data set that you could build off of. Once you have that, right, this integrated model, the running of a bunch of algorithms is easy. In fact, this is one of our prior PhD students' research, he was able to run hundreds of different types of algorithms, rule-based, statistical, machine learning, simulation-based algorithms that utilizes this integrated data model that is generated by researchers over many years. And you can now put that into action and see whether you can identify faults in the facility. So we turned that approach of going towards the self-managing HVAC system into a product and basically utilizing the digital twin as the main component of the product and using that to run a lot of AI, in this particular case, hundreds of AI algorithms to be able to do fault detection. And the benefit that we have observed in these cases is that you not only, of course, see things spatially, you can say, okay, here are all my faults, but when we describe the faults, we don't just say, oh, there's something wrong with air handling unit 1. And then all the facility managers need to deploy a bunch of workforce to figure out what is wrong with that unit. Instead of saying that, we're able to do root cause analysis. So we can say, because of the digital twin that's in there, right? So we can say, okay, the heating valve is stuck to close in this particular asset. So you can go to that particular asset and you know exactly what to fix. In addition to that, because we did have the digital twin there, we can identify the energy savings, right? So we can do simulations, thermal models, and say, okay, if you fix this problem, this is the amount of energy that you can save on a given day. So it helps the facility managers to prioritize things. And on top of that, explainability is very important when you're trying to sell a product to facility managers, right? Nobody wants this black box thing that is just generating all sorts of data. So here they can click on a specific fault and it will take exactly where the fault was identified, show the raw data, and using that, the facility manager can say, oh yeah, I agree with this, or I don't agree with this, right? So there's always human in the loop, but they don't have to spend time to figure out what is going on, right? These are all provided to them. And this, this approach automatically, identifies 30% HVAC energy savings in 1 month of utilization, right? So that's the power of AI that is combined with contextual data. So as I'm ending my talk, I want to bring that domain knowledge models are at the crux of AI. And even the purely data-driven, there were several waves of AI. The initial AI wave was around expert system. The second AI wave was around all these data-driven approaches, a bunch of data utilized blindly. And the third wave of AI puts the contextual models at the crux of everything. And these contextual models are the domain models. And that's why it's so important to have domain folks, domain experts working closely with the software developers to provide these powerful AI solutions. So we've been using these approaches for buildings and habitats, not just on Earth, but also in Mars with a recent funding that we received from NASA. I just want to put it out there in case there are some possible students out there who want to join our team. We're looking for PhD students and postdocs. And I want to thank all my students and thank you all for your time.